For now, let's take a look at lecture 25. Like I said, this is not a very popular um, um, paradigm to have. In programming, you probably don't want to do that. So this defeats what we call, one of the first major principles in OOP is data encapsulations. So friends feature allows you to bypass the encapsulation, you can access it. So why would you have a data encapsulation to begin with, right? So this is kind of a backdoor access, an afterthought to an OOP principles. So that's why you don't see this friends stuff anymore in the more modern OOP languages like Java. Well, C++ is still modern, right? I don't mean to say that C++ is not. So we're going to talk about polymorphism. Let's just jump straight to it. So after the completion of this polymorphism, I will take questions, but that should pretty much complete the lecture for this semester. Okay, so let's talk about this. This is in review. Actually, no, this is friends necessary. So we're not going to talk about this, and we're going to bypass all of the friend stuff and jump straight to polymorphism. Okay, this is also a dynamic. This is one type of polymorphism, a project overload, operator overload. But let's talk about polymorphism, and maybe if you have time, we can go back to this one. But this concept is a little, a little different than some of the other concepts that I want to talk about. Okay, so in the past 3 weeks, and I believe we started talking about data encapsulations 3 weeks ago. We covered that, and we know what that is. We went through inheritance from last week and also this week, right? And the third part of OOP is polymorphism, the ability to assume different shape, different forms around time. So this is what we call late binding. So if you look at the entire data life cycles of your code, let's say if you have a C++ code, so half of the time it's going to span in this area. Okay, so this is a timeline, right? Timeline from beginning to end, right? This is the entire timelines. And this is the very first stage. It's what we call compilations, right? Compilation is the three process, right? Preprocessing, definition, compilations, and linkage. So this is what we call compile time, right? Compile time is what we call early binding time. On the other hand, if you get into runtime, this means you have the object and linkage already, have the executable ready to execute. You can run it. This is what we call runtime. So runtime is also called late binding time, right? And this is the reason why you see this late binding right here. Okay, late binding. So the ability to assume different shapes. So this decision for this particular object to assume a different function is a runtime behavior. Okay, compiler does not know. So this makes polymorphism super, super important because nowhere in the computing history prior to C++ could you have the ability to have your code to decide what a shape or a set of behavior and shape to assume, right, at runtime. So computer makes a decision for you, right? This is very powerful, man. If you don't do that, then you have to instruct at compile time what this object's behavior and properties should be, right? This is what we've been doing all along, right? Compiler sees the logic, and you know what those logics are, right? If else, right? If this, that, and then you can get this properties. If not, then you don't get this property. So this is what I meant by that sort of decision. That sort of decision in polymorphism is done at runtime, and this is super powerful. So this thing, function overloading. Okay, so function overloading is it's what we call a behavior that could be manifested at runtime, and this function overload or method overload actually. It's a hey guys, I'm stopping for a while. Let me just summarize this, okay? I know this might be a little confusing. Now, when we're talking about polymorphism, it is not only the runtime polymorphism. You can also have what's called compile time polymorphism. Okay, So polymorphism, the ability to, to assume different shapes and forms, or be able to decide on what method to take on next, could happen at compile time as well as runtime. Now, this late binding portion is what we call the runtime stuff. Now, your function overloading, this function overloading is an example of what's called compile time polymorphism. I know it's confusing here because I put them under compile time, right? So if I can annotate this, let me do that. So you'll see, let me use a different color here. This function overloading, this one is compile time. Okay, this part is the compile time polymorphism. So basically, what does that mean, right? This is where compiler determines which of several identically named function to call, right, based on the function's arguments. Okay, so you can have function overloading like this. You can also have this is one method of those. There's also another one. I say you can have a function, right, that we went through before. Their signature look exactly the same, with the exception of one function, I say function A, having more arguments than the other one, or maybe even the type of the arguments are different. One of them takes in an integer argument, and the other one takes in string argument. Those are what we call function overloads, and they could be they're basically a part of your compile time polymorphism. Okay, runtime polymorphism is the ability to determine which class, which behavior to take. That is actually a little more advanced. And I believe after this, in the next page, we'll talk about runtime polymorphism. Okay, so just remember this very first part is compile time. Okay, all right. You guys have any other questions? If not, then I'm going to move on. Okay, with the recording. These are actually methods. Okay, they look very, very different than a method because they're what's called operator plus. If you recall in the previous slides, actually page, that portion that we bypass under a friend, that's actually when we do this. So these plus in context of the string, right? When you have to, this is actually a method. So this is a function overload, which is a compile time behavior. Okay, so when I said runtime behavior, that's not correct. Subclassing and subtyping polymorphism. So this involves virtual table, virtual keywords, late binding, C++. There's actually a couple of questions about this on your quiz. So let me kind of get into this, right? So polymorphism has basically two types. One is the static polymorphism. One of them is called runtime polymorphism. So this static polymorphism the behavior is pretty much determined at compile time. Static is compile time. It's an early binding. Runtime is late binding, and it's dynamic. Okay. All right. So this subclassing, subtyping polymorphism is the most important of all because this involves runtime decisions. Prior to C++, object-oriented programming, there is no such thing as runtime behavior, right? You tell a computer to execute a function, and the function executes a set of a logic, but the function is not going to call another function, because the object that this function is associated with it, which is called method, tells it otherwise. So there was no such thing, right? Subtyping, subclassing polymorphism until C++. So we're going to spend some time talking about the second half, which is the runtime behavior. Okay, so this is polymorphism. Let me just use the point and circle examples here, right? So what I have here is a base class. This class definition is a point with an x and y plus the area calculations. So if I do circle public point, so what I'm doing is I create a subclass called circle. So this point is your parents superclass. This is your subclass called circle. Okay. Now this circle is going to inherit stuff from your point because this protected x and y will be available in C as well. Okay, so this x and y plus the area, right? Area is definitely going to be in there because area is a is a behavior. X and Y are properties. Area is public. X and Y protected. So C is going to have that. Circle is going to have that. And circle is also going to have its own radius. And this one it's a floating property. And also this flow area. So this flow area is circle's implementation of area. And this overrides the flow from overrides your point area. So whenever a child or subclass decides to override, right, the parents class, then the behavior of that particular method will be completely replaced, right, by its own custom logic. So it is very possible that circle wants to override it. So it's not like when a subclass inherits some trait from P from parents, that trait can never be changed. No, you can change that trait as well. So this is the power of polymorphism. Okay, this is the power. This is the power of inheritance. So in addition to inheriting a trait, you can also override a trait. Okay. So in summary, circle has everything that point has, which is true, including its protected member, which is true, X and Y, and access to public method area, which is true. Okay. So what is not said here is circle can also overwrite or replace the prior definition of your or decorations and definition of your area methods from point. Okay, by replacing it with its own custom logic. Okay. Any questions about this? This is the beginning of polymorphisms here. So we're going to spend a little more time trying to understand, with some use cases. Okay, so polymorphism circle and point definition. Circle inherits on point, right? We talked about that. Circle has all of the data functionality, point, yes, because everything in point is either protected or public. So good, circle has everything. You can add new data and methods in a circle, and we saw the example of the area one. So area for the circle implementation is obviously radius times pi, right? And point is 0. This is circle's attempt to override the area part, even though circle inherits basically the entire signature, but circle has the ability to override parents' behaviors. And the above definition are very, very specific. So let's talk about the very next one. Okay, so this is the full implementations from beginning to end. Okay, so what we're looking at here is your class definitions with is X and Y, right? So this is the setter. This is a setter, a parameterized user-defined constructors. And circle has its own parameterized or user-defined constructor as well. So basically what this is saying is in addition to having access to X and Y, circle also has this radius and also this is Boolean circle thing. And basically what this is Boolean is used for is for ascertaining in the computation of area if is circle equals true, which is true because in circle there is this is circle, right? And this is circle upon construction of your circle has already been set a Boolean. So this Boolean is already set here. So when you do this, right, when you write circle C equals new circle, and you use the custom constructor, you can pass in a radius plus true, right? So if you do that, you're creating an instance of a circle that claims itself to be a circle, even though circle is a point. But in this case, this is circle in the area. It's going to tell your object at runtime to check, hey, are you a circle? Yes, right? And that is going to return this, right? Okay. Well, if this object, because we don't know if this object is a point or circle, right? When you do something like this, the very first thing that happens is a point is created. Okay. There's actually a point. So what is not displayed here, and this is very, very tricky, is at compile time. Okay, at compile time, your code, your compiler supplied a point. This one is implicit. Implicit meaning you don't see it; it's hidden. But it actually supplies a call to point. Okay, and you use the point class operator, scope operator. to call point generic or the default constructor, okay? Because the fact that you don't see it. In this case, we are not doing it. We explicitly calls points default constructor. Okay, not default constructor, custom constructors. But if this one does not exist, okay, I just want to be super clear, then by default, there is a default one that is implicit. If this one is hidden, that is automatically supplied at the very beginning of this circle constructor. So this means that P is always created before, ahead of circle, okay? So when you do this, right, when you do new circle, two things are created, number one and number two, in this order, okay? This is what happens when you issue a statement like this, that the entire thing like this is created, okay, in that order, 1 and 2, okay? So this circle C also carries a link to this parents class. And this is the reason why, you know, at creation time, you tell yourself basically setting a flag to if circle equals true so that you can return the correct area. Because if not, then by default, C has access to points, right? Point area, because area computation is public, okay? And you can access that way, right? Explicitly using what we call a point, a class scope, to say that circle, you know, this is the circle area here is actually a point area, right? Because is circle is false, right? Does it make sense? So by default, if you don't specify a value associated, actually, what's not good here is you have to say this one equals false by default, right? Because if you don't do that, then in C++, it's very dangerous. Each circle doesn't have any value associated with it, so it could be anything. So you want to make sure default circle is false. Okay, and then once circle is created, then you know this one is true. Then in that case, you know, you can move on with it. Does it make sense so far? So this allows you to kind of navigate, right, at runtime. So this behavior, it's kind of you know, it's not automatic, right? You have to manually specify this type of thing. But this allows you to access, right, from your child into parents. So this behavior is possible. Like circle has access to point because through inheritance, circle is a point, okay, is a point. So this is a relationship, as we spoke before, manifested in polymorphism, right? So this allows you to access from child or subclass into superclasses. Do you guys have any questions so far? So this is one example calling for a point, circle points. So let's talk about this, right? This one, now that we've looked at, you know, this code constructions here, let's take a look at the console behavior. So in the console applications, I'm creating, and this is a static static instantiation. The memory is consumed from your stack. So this point, it's calling its default constructors here by instantiating a point object. So this point object is created, and then you can do px and py, right? Can you do that? Well, let's take a look at x and y. X and y's are both protected, which means a point has access to it, right? An instance of it can have access to it. So this will give you the x and y coordinates and also the area associated with this point. So there's no problem here whatsoever. Does it make sense so far? You can do the same thing with C as well. So circle has a default, a parameterized constructor that takes two arguments, right? This is radius, and this is each circle, right? So you can print itself. So x and y are both from your point. Well, circle doesn't have x and y, but circle inherits, right, from point. So when you do circle C here, what happens is your P is going to be created first, the point, and then circle is created, okay? So this is what happens. Circle with radius 2 here, and x and y would have been inherited straight from your P. But by default, I believe x and y for P is 0 and 0, right? If not, then you're going to get into an issue. So let's take a look at it. So in this case, this is going to be an issue here because when you call, actually no, because when you create a circle with this thing, you're also setting the point. So this means that this is inline initialization, okay? List initialization means, I think I also went through this about 4 weeks ago. When you invoke this method, you can also initialize. This is through the list initializations, list of things. In this case, what you're trying to initialize is the constructors here that has this one with x being 0 and y being 0. So this circle constructor takes care of the point. So this is precisely the reason why when you create this, you have a p already, right? Your point object is already created. And because the point is already there, when you do c.x and the scope for x and y are both protected, you can do c.x and c.y. So this is going to give you 0, 0. Okay, and when you do c area, the reference, the object that you have to look at is c. C is what? C is a circle, right? So this area, when invoked, it's going to be based off of whichever object that is invoking this area. So this object is a circle, then the circle area is going to be invoked. Does it make sense so far? So this is very straightforward. When you invoke an area, right, this method has to be a part of that object. And what is this object P? This object P is a point. It's a point. So this P's area, right, points area is going to be called. In this case, C.area is going to call circles area. So there is no polymorphism here, right? C is calling C's area, P is calling P's area. So everybody's got, you know, their boundary very well defined. So this is all cool. And what is going to be interesting is the polymorphism I'm going to show in the next, okay, in the next slide. Okay, so it looks like, you know, the Poppyian behaviors, when you're doing it, when you're trying to invoke them, you always have to go back to the object that where this is belong to, right? So the only polymorphism I say in this case is kind of like, this is not polymorphism by inheritance, is C calling X, because X it does not exist in C inherently. So C is actually calling, right, the parent object. C actually has that through that inheritance here. So, but still, I mean, this is inheritance. This is not polymorphism. Polymorphism is something like when you call area on C, this area gives you this point area. Does it make sense? That is what we call polymorphism, the runtime behavior change. Okay. So let's look at this one. Okay, so here is the beginning polymorphism. When you have a inheritance structure that looks like this, okay, you can actually, what you do is you can create a point object just like this, okay? And this is very straightforward because this means that this P is an object of new point. It's an object of point. But you can also do this where this P is actually a circle, okay? This is what we call is-a relationship because is-a says that this particular P is also a circle through this inheritance. First of all, you have to set this up and say that, so actually what happens is this portion is what we call a dynamic type. And this is what we call a static type. This portion right here is what we call a static type. So what is dynamic type? What is a static type? Well, dynamic means dynamic memory allocations. So this new circle is allocated from your heap. Now this point P is allocated from your stack. Does it make sense? So if you go back to, I know we went through this painstakingly the other week, I think 4 weeks ago. This stack right there is your point P, okay? This circle right here, dynamic type, is coming from this area, like this small portion here, okay? So, and this is heap, okay? And this is stack right here. This stack is the dynamic type, okay? And that memory is coming from stack. Okay, so On the one hand, the left-hand side, you have a static type. On the right side, you have dynamic type, okay? And the reason why you can do that, point P equals new circle, is because the circle is the type of point, right? And point is a type of circles. So this is what we call upcasting, because you're casting the circle into a point. A circle is a point via public inheritance, right? So you gotta look at is a, right? The directions that we have before, where we have P, right? And then you have, remember there's this open arrow, right? And then you have circle down there. So you have to follow the circle and name it. So in English, okay, this relationship is called is a, right? Is a relationship, okay? So the English translation, when you have something like this, sorry about the key terms here. Okay, so now you can see. The way you would properly read this is circle is a point, okay? Circle is a point. So given that a circle, right, which is newly constructed, is a point, then you can assign, right, a circle to be the label. Even though the label's point, this P actually points to P, not a circle. Does that make sense? So what does that mean when you call P area? Now P is a pointer, right? So you have to use the array arrows. You cannot use dot operators. You have to use array. So this is the reason why you have this. Okay. So P area. Do you think this P area is going to call points area or circles area in this case? I can tell you this area now points to circles area. Why? Well, P, right, is based off of, you gotta always look at the dynamic type. In dynamic at runtime, is P pointing to P pointer itself, right? Point itself, or is it pointing to circle? In this case, P is pointing to a circle, okay? And this is the reason why P area is calling the circle area for you. Okay, there's a couple of other provisions here, but I wanted to make sure that you understand this. At runtime, you look at what is the dynamic type. If this dynamic type that the P is assigned to is a circle, then yes, this P area is going to call the circles area, not P's area, right? But P, in this case, is pointing to a point. So dynamically at runtime, your P is going to be pointing to point area, not circle. So this is what happens with polymorphism. Sometimes when you see a P here, and you don't just look at your static type, you look at your dynamic type. Okay, so this is the power of the polymorphism, because dynamically you can assign P to a circle or point, right? So this can mess up a lot of your logics if you don't understand what it is you're doing. Yes, then you can be a problem. Dynamic memory allocation involves pointers, and therefore you use these arrows. A pointer can be reassigned, right? So this is the dangers in playing polymorphisms here. If you reassign a pointer to a wrong type, either you get code crashes or something that does not work or does not give you the correct value that you expect, right? So this is polymorphism in its upshot. So let's take a look at a specific examples here.
Like this part, right? This is polymorphism here, okay? Sometimes this point, whatever you have here on the left side, could also be an interface. And this is totally allowed, right? We have interface in a concrete class on the other side. But what's on the right side, though, in this case, would have to be, a concrete class implementing, right? That implements point. So that is possible in Java. So interface polymorphism, you can actually look at it, but there's no such thing as an interface in C++. Okay, so this is only available when both points and circles are both what we call concrete classes. So in this case, point is the base class, and circle is it's a sibling, okay, class of that. So that way you can create polymorphism here.
So this P area is very straightforward, right? You look at P is part of a point, so it's pointing points area, right? So there's nothing wrong here. Okay, so this is all good, right? Points area. What is this P? Well, this P is pointing to a circle, but this object still points to points area. for some reason, right? And this is, what does that mean? Well, that means you're not really, I mean, there's something wrong with the, or maybe there is a provision that we don't see here. And this is what we're going to investigate here, okay? Now, what about this? Well, this is dynamic. This is not dynamic. This is all static, right? You're assigning using the object references. There is no dynamic pointers here, and because this is not a pointer, you can use the dot area. So this is static allocation, which is very similar to this. And how about this? Well, this one is statically allocated, and you're saying that there's P is a reference to C. If P is a reference to C, P is C, right? When you are using the object reference, creating a reference P to C, you're still calling P's area here, okay? Even though so basically what you're looking at is the object that this P is pointing to. This P, there is no polymorphism here. It's just simply saying, well, P is a type of point. So even though I am C's alias, when I am doing a P dot area, I'm still getting points area. What you can do is you can run through these examples at runtime and see for yourself to see if P is pointing. So you can use the same code that we displayed before to see about this. Okay, so let's talk about. So there is a question mark here and see if we can answer this and resolve this. There is also a project reference here. So basically, the summary is if you have this type of assignment, and given the fact that P, circle is P, so you can do this assignments here, but still, by and large, you look at what this object is originally, right? This is not dynamic here. This is static, right? Static assigned to static, so nothing changed. So there's no questions about this. So we know because there's no dynamic type, right? Circle is not dynamic type here. So this P area, it's still points area. And again, there is no dynamic type here. So this is all static. So P goes back to what is type. And there is no obviously questions about this either because point is really the point. So P area is the P area. Now the question is the second one, right? That you have a dynamic type, which is a circle. Now, how come P area is not pointing to circle, but pointing to P, right? So let's see if we can do something about this. All right, number 2, just bear that in mind. This thing is what we call virtual table. And this is really the last part of polymorphism here. There's virtual, there's pure virtuals. So the motivations here is that, if I have something like this on the very bottom, right, point P equals new circle, that I wanted to invoke polymorphism. Polymorphism, I want to be able to change, meaning if I do P this area, I want to call circles area, okay? I don't want to not point area, okay? Now this is polymorphism because P is pointer, it's a point, but P is not a circle. So in order for that to be the case, what you need to do is to set a keyword virtual, okay? This keyword virtual means that at runtime, when you call P area, this one is going to go into a point. Your point object sees that this area is declared as a virtual. So virtual is a keyword to bypass. Okay. Do not use my. Okay. My is virtual. Use your subclasses. So in Java. Java completely got rid of the virtual. It automatically defaults to dynamic type is the one that governs the behavior of your static type, right? Dynamic type is the right-hand side, right? Static type is on the left-hand side. But in C++, you have to manually institute this in the base class that this area is a virtual. So virtual doesn't really mean that you can't implement. You can still implement this, okay? You can still define this area in point, but virtual is a keyword for bypassing not to be used in the event of polymorphism. So polymorphism means that this static type is assigned to a different dynamic type. That's the cue where you have polymorphism. So this allows you, if this is a virtual, then P area is going to call circles area. And this is the requisite, okay? So if I were to summarize this, and there is a summary right here, that P is a static type and circle is a dynamic type, and P invokes a virtual method that is overridden by subclass, then the subclass versions will be installed. So this is the complete behavior in summary, right? In order for P to invoke circles, P's, right? The first thing C++ is going to look at is P is point, but point also has this virtual thing. So when I invoke that area, P area, because this is virtual, I'm going to bypass it. The subclass version will be invoked, and basically that virtual method is meant to be overwritten, right, by the subclass, and the behavior of that area in the subsequent dynamic type will be invoked instead. Okay, so what does that mean? Well, polymorphism means the behavior of this object, right, which is P area, is not really what it means to be, right? Through polymorphism, it's pointing to circles. But because, and this is only possible when you have inheritance structures here, where P is the base and a circle is the subclass. Okay, this is only possible when you have something like this. So first you have to have inheritance, right? Second of all, you have to write code in this fashion where you have dynamic type and then static type. And the behavior of that P object is going to switch to the circles behavior. Okay? Yeah, I mean, this is what happens if point of area is virtual, as you can see here. By having this we already know. This is good, right? So point is pointing to point, so this is no problem. It's more about here. This is polymorphism here, okay? This entire polymorphism is the second example here, where point P equals new circle, and this area, P area, is actually calling circles area. Because what happens is P goes into its own flow area and see that, oh, this is virtual, so I need to bypass. So that virtual, this is what we call virtual table. So there's a virtual table that associates children to class, to parents. And these virtual table says, it's basically like a routing table, a PO box, you know. When you say this is the PO box 710, that direction, the mail delivery is gonna go, it's not gonna go through PO box 123, right? It's gonna go straight to 710. So that routing table at runtime is called, we call virtual table. And this virtual table redirect this area, it does a round trip, and then it goes back to circles, right? It goes into the virtual point object, and it sees this virtual, and it says, no, the redirect, you have to be redirected to circles area. So this whole behavior is what we call polymorphism.
So runtime polymorphism only works when an overridden member function in a base class, right? In this case, the base class is point. Only when the member function in the base class is virtual. Okay, does it make sense? Runtime, let me repeat that again. Runtime polymorphism only works when an overridden member function in the base class is virtual. Okay, so a virtual function is a member function that may be overridden in a derived class, in a runtime dynamically allocated derived class that is used for runtime polymorphism. Okay, so what is a virtual thing? What is that thing? Well, to implement virtual function, what happens is your compiler, okay, creates what's called a virtual table. A table with all of the virtual function and there's pointers, specific memory address. What does that table do? That table allows the computer to quickly look up, right, which function to call at runtime. This is the reason why the lookup is so fast, because compiler has built in this virtual table at runtime in memory on a stack, right? Right? Remember, stack memory retrieval is very, very fast, okay? To allow a dynamic object to quickly fetch the stuff out. So the virtual table contains an entity, basically an entry for each virtual function with a function pointer that points to the most derived function that is accessible, right, to each class. Looking up which function to call makes runtime polymorphism, basically slower than compile time polymorphism. But then again, that is the cost, right, to doing it, from your heap versus from your stack. So that's the point I'm trying to make here, and this virtual thing is very important. Now you don't see this virtualness in Java. Okay, Java got rid of these virtual keywords and whatnot.
You can see that point is point, right? So when you are calling P area, wouldn't you be calling points? No, in this case, it calls the circle area by virtue of the same argument as the above, right? Polymorphism manifests itself. So polymorphism is only possible, right, when you have virtuals, when you have virtual keywords attached to any of these behavior that needs to be overwritten at runtime, that behavior changes. And sometimes you'll see when they define virtual, and this behavior is set to 0. This is what we call pure virtual. So pure virtual is to be implemented by subclass. When something is virtual, you don't have to implement it, right? There is no necessities here. But when something is pure virtual makes this class pretty much abstract. You can't just instantiate this one. A class containing one or more pure virtual is called an abstract class. So abstract class is something that you cannot create. You cannot instantiate it. So this means that when a pure virtual exists in a class, that class is meant to be inherited. Okay, so this makes it a kind of a mandatory thing, and that is kind of a difference between virtual versus pure virtuals. So in this case, Circle has to implement it. No question about it. This makes it mandatory. See, before, if you just make this a virtual without this equals 0, then this Circle doesn't really have to implement, but now it has. Okay, so this means that not only will this area not be looked at, that when you have polymorphism is definitely going to be calling this circles area. And the other problem is if your circle, just take it for granted and say I have an area here, but do not implement it, this is a runtime error. So there has to be implementation of this flow area in Circle due to the fact that this is virtual. This is pure virtual. Okay. So that's what I wanted to say about polymorphism. This is just an application, right, of polymorphism, making a class abstract. So in Java, there is an abstract class, this keyword called abstract, but there is no such thing as virtual, pure virtual. Both of these are only available to C++. And we talked about how you can make an object behave differently through this runtime dynamic polymorphism. The dynamic polymorphism in addition to this virtual keywords. We also talked about inheritance, right? What is available, what is not, through different access modifier. Protected, public, all good. Private, no good. And then we, by and large, talked about when an object behavior or property is invoked, in addition to the data encapsulation constraint, we also need to look at the base class that this object, right, or this reference or pointer is based out of, right? So we go back to the points, right, in this case. So the point area needs to be invoked. The only difference is when you have polymorphism where the virtual keywords is assigned in the base class, that redirection at runtime happens. And that is the power of polymorphism. I can give you a lot of examples out there. You might be wondering, Professor, why do we care about polymorphism? If you want this object, just instantiate the object, right? Do that, right? Well, inheritance is not that simple. When you're using inheritance, you're not only just saving code or making the code a lot easier to read, but a lot of times you also want the flexibilities, right? So have an object to go either ways. through this pure virtual gives developer essentially the tools to make your code flexible, right? As you can imagine, having a rigid set of logic to govern behavior is a very taxing things, right? At runtime, you have to write a lot of if and else or switch case. Polymorphism totally eliminates the need of having to do it because developers knows that runtime, if I make this in virtual or even or even a pure virtual, right? This will give me an entirely different set of behaviors. It basically gives me the tool, an arsenal to make my code flexible, right? To behave in that directions, not this directions, right? So this opens up to lots of possibilities and flexibilities, and also the decision making, offloading decision making from compile time logic to runtime logic.